Va bene?
Qualche minuto.
Devi far partire la registrazione.
Ok, sì, Matteo, puoi far partire la registrazione. So, welcome everybody. It's a pleasure to welcome in particular our guest today, Stefano Covino. Stefano is a primo ricercatore at INAF Observatory of Brera since 2017. He got his PhD in 1995 at the Università degli Studi di Milano, and supervision with Laura Pasetti and Sergio Ortolani. And then after a few years postdoc, he got a staff position at the Observatory of Brera. And Stefano has a wide experience in astronomy, covering many research fields, in particular multi-messenger astronomy, time domain astronomy, electromagnetic counterparts of gravitational waves, high energy astrophysics, GRB, AGN, and instrumentation. Today, Stefano will talk about BLAZAR with a seminar entitled BLAZAR High Energy Periodicities, a Cautious Approach. So, Stefano, I give you the microphone. I'll inform you when you have 5 minutes to the end. Please mute your microphone, everybody, and please, Stefano, you can start.
Okay. Well, thank you. It's really a pleasure to be here virtually with you friends. This talk is supposed to be, the title explains clearly what I'm mentioning, what I'm discussing. However, anytime you have to discuss about time series analysis or problems related to periodicities, it is very easy to understand that it is a very complex topic, and I am prepared this talk in order to be somehow didactic. I mean, it can be followed. It is supposed to be followed even by people without a specific knowledge in the field, or at least just some direct experience. So, no problem. It is an activity that produced in the last few years a couple of papers, or more than a couple of papers, several papers, and it is an activity carried out with Angela Sandrinelli, Marco Landoni. Recently, he joined our small team, and Aldo Treves, who is essentially the one who had the original idea, let's say, in order to try to study this problem. So, why we decided to address the problem of possible periodicities in BLAZAR, or in general also in active galactic nuclei? Well, first of all, as you know very well, we have a huge amount of data about this category of sources in essentially, I would say, any band from a high energy. Now we have Fermi, wonderful machine, giving us a huge data set for essentially everything emitting high energy radiation in the sky. We have a rather efficient network of optical telescopes, providing, at least for the brightest sources, a very impressive coverage, although, of course, given that the telescope is on the ground, you have periods without the possibility to observe, and, of course, radio and any band is covered. Actually, I don't know how you are confident with BLAZAR or active galactic nuclei physics, but these are the typical sources observed with a multi-wavelength approach, essentially because they emit in any band, from the radio to the gamma ray, at variance, for instance, with many other sources, stars, and so on and so on. And in particular, there is actually a huge literature, because the blazars, now let's speak about blazars, but this is true in general for active galactic nuclei too, although there are also differences. These sources are very variable. They are variable with essentially any time scale, and just the study of their variability is a very powerful tool. I reported here 3 papers chosen randomly, so they are not supposed to be the most interesting or the most important, but they have been published, in the last 1 or 2 months when I began to prepare the slides for this talk. So this is just to allow us to understand the level of activity that there is in the community about the study of variability for these sources. Variability, it's probably useless to stress, but studying the variability, you can draw inferences about the physical mechanisms driving the emission of these sources, and also you can have some idea about, it depends on the specific case, about the geometry or so on. In the specific case, what we decided to study with some more detail is the possible existence or presence of quasi-periodic oscillations in AGN and or blazars. Why there could be these QPOs in this kind of sources? Now I'm not really discussing in a detail the possible physical mechanisms driving periodicity or quasi-periodicities in their emission, but in principle there could be many explanations, many hypotheses. For instance, we have, as you know, the emission from these sources is driven by accretion around a central massive black hole. But in principle, there could be binary black holes. This is entirely possible. And the possible binarity of the black holes can produce, depending on the specific mechanism that you are studying, some irregularity in the emission from due to the accretion, and often an irregularity that is actually rather regular, if you allow me to play with the words. So with some real periodicity. But there are also other possibilities, like transient periodicities that maybe can last for centuries. Of course, transient or regular depends on our observational time scale, but these sources could well have much longer time scales that compared to what we can actually study. And irregularities in the accretion can easily generate irregularities in the emission, and these irregularities can be more or less periodical. So there is a huge activity, not only observational, but also theoretical, from the theoretical point of view, and there are many authors that tried to address this problem, in particular because in the last 5 years, maybe a bit more, 10 years or so, there are many, well, not so many, but several papers claiming to have found real periodicities, or in a large fraction of cases, hints of periodicities from these sources. And now let's try to better understand the situation. If we think to a periodicity like, a variable star, we have to forget it, because these sources are hugely variable, as I said before, or wildly variable. But it is entirely possible that together with some intrinsic variability due to the accretion process, for instance, or to the generation of the jets that the emission of which is what we observe in BLAZAR, there could be some more regular oscillations. And there are several cases identified in literature, BLAZAR, several AGNs, as you can see. Probably one of the most discussed and definitely one of the most interesting is 1553, PG1553+113. that shows a rather interesting regularity in the active states in a flaring activity. Now, therefore, we decided to try to address this.
Stefano, sorry.
What happened?
Is it me or everybody seeing always the same slide? Are you showing always the same slide? Does anybody see the... Are you still showing the variability as diagnostic tool?
Yes.
Yes.
Yeah. Oh, now you change. Now you change the slide. Yeah. Now I see. Yeah.
So
that's quite cool.
So at some point I was curious, and then I went to ask to Santi asking if it's a problem with my laptop or not. But
no.
Yeah. So
now the slide should show QPO in AGN.
Yeah. Now we see that.
now,
Okay.
yes.
Okay, that's curious. I don't know. Anyway, okay.
Can you show briefly the previous one, just very briefly?
Yeah, I agree with that. If it's possible for you to show
Okay,
Yeah.
this is the second, just example of light curves in many
No,
bands.
blocked again.
But
We still see the first. Yeah. Now we see this the slide with the BLAZAR and AGM variability.
so there is a long delay in changing the slides. That's okay. Let's do this way. Anytime I change the slides, I ask you if you see it or mention the title or whatever, just to.
Okay, fine.
That's quite curious. I don't know exactly. Anyway, I was discussing these slides where you see light curves from a paper by Sandrinelli, from a paper by Stamera, and from a paper by Graham. I don't know if you see them. And actually, these are just examples.
Not yet. We are now on KPO in AGN and blazars.
Oh, yes. Look at the with the question mark.
Yes.
Yes, it's the first of the two.
Yeah, now we see the right one.
Would you like I try to share the PDF rather than the keynote, maybe?
It's up to you. Maybe if it's better, you can try.
I tried. No problem at all. Please. Do you see my
Yes.
screen? Now you should see, I hope.
Yeah.
Yes. Now
QPO in.
Sorry, my mistake. Okay.
fine.
Yeah. Now we see Sandrinelli, Graham, and Stamera.
Hey, maybe it's better with the PDF. I don't know exactly what was happening. Anyway,
Okay.
that's not important. So essentially, as I was trying to tell you before, the idea we had the idea to try to study this problem as other teams in the literature, and if you begin to study this kind of mathematics, because finding periodicities is exactly part of it's a topic, an important topic of the time series analysis, and this is essentially pure maths. You immediately see that there are a large zoo of possible tools. I'm not discussing now, of course, all these possibilities, but in its essence, it is important to remember that when you have a very powerful signal, I mean, again, a variable star where you see the periodicity by eye almost, or you can use any tool you like, but typically if it is a real periodical star and the sampling, the observations are good, you immediately see this periodicity. But this is exactly like if you are detecting a star with a very high signal to noise in a CCD frame. It is easy. You can discuss forever about the best tool to detect point-like objects, but when the signal to noise is high, any tool is equivalent. The problem, the problem becomes difficult or even interesting, if you like, when you are trying to detect something that is close to the 3 sigma formal limit. And then it is also important to remember clearly that any different tool is not usually really equivalent, because essentially saying that you have found some signature for a possible periodicity in general means that you have to you compare a basic hypothesis as usual, and you might say that the basic hypothesis is consistent with the data, or it is not. And the basic hypothesis is usually that what you observe is just due to noise, essentially. When I say noise, I will clarify what I mean, essentially just to have a common vocabulary. The main tool that we applied in the first case, but I will discuss other things later, is a standard Fourier analysis. I don't think I have to recall much about this basic mathematical tool that we study during our university courses continuously. And essentially what it is important to remember is that with the Fourier transform, you are simply converting your signal in the time domain to the frequency domain. In principle, you have exactly the same amount of information, but working in the frequency domain can make, depending on the specific case, things simpler. As you probably know, we in reality do not have an infinitely long time series, and we anyway have a sampling. So essentially what you have is what we call the discrete Fourier transform, and there are many important theorems that I'm just mentioning without discussing. And for instance, you can, depending on the length of your time series and on the sampling, let's now think to have time series sampled in a very regular way. So maybe an observation every day, every week, or whatever you like, but without deviations. And then you can have information for a number of frequency in the frequency domain that are also known as Fourier frequency, simply. And you have a maximum frequency that is also known as the Nyquist frequency, and you can have information, any information about your time series at frequency higher than that. But this is not definitely really important. It's just to know what we are discussing about. Now, I mentioned something before that is the key of the problem in analyzing time series of a blazar. And the problem is the noise. In many cases, even in astrophysics, again, often, not always, but often, if you are studying a variable star, the light curve of a variable star, you may assume that you have noise independent of the frequencies. So the noise, it is also called, known as white noise. This is the simplest, the most simple case, and this is the one that we usually study on textbooks. But actually, the problem is simply that in the reality, in the real world, noise is not white very often. What does it mean that noise is not white? Well, I got on the web this cover of a CD, the kind of music that is supposed to relax you if you hear it. I never tried, I don't believe, but anyway. And it's probably the author of this cover was a nerd. I guess I would bet about it. And however, it can be useful because you see an example of white noise. Essentially, at any frequency you are studying, the noise is the same, is independent of the frequency, and then you can have many other possibilities. And in particular, in astrophysics, the important is the pink over red, or even called brown here, I don't know exactly why, noise. It's a noise that increases going to the lower frequencies. As you will see, this is very common in the light curves of the AGN and blazars, and this makes any analysis a real mess, if I can say this word, because essentially this means that the noise is dependent on the frequency, and there are many nasty phenomena that can create, or better, pretend periodicities that actually are not real, are just an artifact of the interaction between the noise and the sampling of your light curve, for instance. Okay, but as I mentioned briefly at the beginning, we are relatively lucky because more than 10 years ago was launched Fermi. Fermi is giving us an amazing data set of observations, and since Fermi is orbiting the Earth, in most cases these observations can be easily binned on a regular grid, and therefore the analysis can be carried out in a relatively simple way. And it is not by chance, indeed, that when Fermi was launched and we began to see many the results of the Fermi observation, so many light curves for several for many astrophysical sources, and in particular blazars, almost all of a sudden there were papers claiming to have found periodicities in this data set. And therefore, we decided to select a small sample of blazars, just 9 objects. This is not an unbiased sample, so we cannot draw statistics from it, because this sample is based essentially on the literature. I mean, there were sources with available Fermi data, and these sources, at least in some of the analyses carried out about these sources, there were in the literature claims of possible periodicities. In a few cases, these periodicities were evaluated with very high significance. In most other cases, the authors just discussed hints of periodicities, but we decided to collect the data for these 9 sources and try to analyze them with a homogeneous tool. In other words, given that in the literature, for good reasons, often there are many different tools, and as I mentioned before, if what you are looking for is not highly significant, any different tool is giving you an answer to a slightly different problem, it is entirely possible that different tools give you different results. So we decided to apply standard Fourier analysis, as I mentioned before, for this subset of interesting objects. Just to give you an example, the kind of data that we had are of very high quality. These are plots taken from a paper by Angela Sandrinelli in 2018. We have PKS2155 and PG1553. We also have the optical data, and as you can see, the sampling is not perfect, but it is not that bad. But in any case, on the contrary, the gamma ray light curve are continuous without interruptions, and so these are the best data for this kind of analysis. Just to give you some detail that probably you are not very much interested unless you are planning to redo the analysis, we chose to use the curves with a 40-day binning. Why such a long binning? Essentially because this improves, of course, the signal to noise of the data, and also because we were trying to study relatively long periodicities, year-long periodicities. If you look at the literature, there are also several papers discussing much shorter periodicities. I don't know, weeks, several weeks, or even shorter. In our case, we are discussing longer periodicities, the typical periodicities of a year or a few years at most, that could be associated to possible binarity of the black holes feeding these objects. And and essentially, a Fourier analysis of this kind of for this kind of objects is relatively simple conceptually. We derive the power spectra, the periodograms more correctly, and we check, as it was done already in the literature for other sources, if the periodogram is consistent as being drawn from a simple power law. That actually simply means pure noise. Otherwise, if we see an excess, this excess could be typically attributed to a signal, to something different. And if this excess is let's say, showing a sort of peak in the periodogram, we can speak about of quasi-periodicity at least. I again spare some detail because if you want to carry out a formal fit for a periodogram, it's quite important not to forget that the statistics in the periodogram is not the Gaussian statistics that we are confident to typically use, unless you can average many light curves, but this is not the case because we were looking for year-long periodicities for light curves that were about 10 years long. So you have to adopt a proper likelihood and so on and so on. And if you are interested, we can discuss this later, but I think now it is not the case. So again, other technical details, because the analysis was carried out in a full Bayesian context, and essentially we derived the posterior distribution of the parameter of the best fit power law for each source, and from the posterior distribution we could essentially evaluate if we observe power in excess of the possible extrapolation to a given confidence levels, 1%, 0.01%, whatever you want, compared to the basic hypothesis. Okay, again, other technical details. There are several papers describing this procedure that was first described by Simon Bogen in 10 years ago, and then was applied by Cristiano Guidorzi and other people in other fields. Cristiano Guidorzi in particular in gamma ray burst. And okay, so just to give you an example for one source, in this case is 0716. What typically you have a periodogram. I will show you later. You model, you fit a power law, and the residuals are supposed to be distributed as a chi-square distribution. In the lower left plot, you see an example. The sampling is not very high, but the data are consistent. Then you can apply typical statistical tests to evaluate the goodness of the fit, like in the plot in the bottom right, where you see distribution derived from the posteriors, and the vertical line that maybe you see, maybe you don't, but that's not important, give you the probability, the chance probability to have the result that you have, or better, how consistent is the result that you have with the observed data compared with the simulation. And in the specific case of a power law, we have a normalization, a slope, and let's say a constant for the power. You see on the top right plot the marginalization of the posterior distribution, and you see that if you have some confidence with this kind of analysis, these are good results. And if you are very curious, on the left you have a trace of the Markov chain Monte Carlo chain, of course, that was used to derive the sampling, to sample the posterior distribution. And after a beginning where you needed to reach the equilibrium, the algorithm works really well. Well, this is a simple problem, a three-dimensional problem, so quite easy to solve it today. And the chain is stable and the results are reliable, and so on and so on. So you might now want to see the periodogram, and you have in this 3x3 plot, series of plots, you have the periodogram for essentially for all the 9 sources that we have analyzed. And in red, you have the best fit power law to the data, and you have the 95 and 99.7% confidence level for a power in excess of what you can expect from a power law noise. This is the so-called global significance, because another tricky point about the time series analysis is that it is different compared to, let's say, if you have, if you are just fitting one of these blue curves, the periodograms, you can easily decide if some peak that you can see. Maybe let's look at the plot for 2155, the one in the bottom middle column. And often the power is in excess of the local noise. But this is a one point. A second question is the probability that this power is not due to chance fluctuation, since you are studying a number of frequency. It's a correction known as Bonferroni correction, or the look elsewhere effect. There are many different names in the specific literature, but it's very important. Essentially, you are repeating the analysis one time for each frequency. So if you have analyze n frequencies, and it's like if you are tried n times to find your effect, and therefore you have to correct for this number of trials. And probably you have already seen, essentially, in no case we see a noise in excess compared to the expectations for, in no case we see power in excess compared to the expectation for a pure noise. Or said in another way, the variability we observe in the Fermi lat blazars is consistent with being due to just random fluctuations, no periodicity, not at all. However, the result is clear. I mean, there are no ambiguities, but there are, on the contrary, ambiguities, because we are using Fourier analysis, we and as many other people before us, in a very difficult context. Essentially, when you are evaluating the significance of some excess of power, you are using theorems that are true holds only asymptotically. In principle, you should have a very long, infinitely long, virtually light curve. And in practice, this means that you should study periods that are short compared to the duration of your light curve. This is clearly not the case. We are studying periods, maybe the longest are about 2 years or even something more, with the light curves that are good, well sampled, whatever, everything is true, but these light curves are typically 10, 11 years long, no more. So we are probably, we are not in the best conditions for this kind of analysis. We can't do different, but this is important to consider. There are also other considerations. If you try to carry out simulations exactly in this case when you have light curves not very long compared to the periods that we are studying. You see that essentially it is still possible, not in a general, the sample. It might happen that you can have a real periodicity, but you don't see it in the periodogram. It is lost in the noise. This might happen. We checked it, and therefore, we are confident to say that these periodicities are not common at all. And this is also clear from other kind of considerations. A binary black hole of the size of the typical black holes at the center of active galaxies is orbiting, is responsible for the emission of gravitational waves that can be observed by the PTA, the PTRA, or other experiments like that. And if you have even a 10% percentage of binary black holes in the core of blazars, of active blazars that we observe not too far from the solar system, even 10%, a 10% percentage would be already too much, since in that case the spectral gravitational wave signal would be higher than what we now know. We still have upper limits, although if recently there was some discussion about the possible detection. But in any case, if there are binary black holes, they should not be very, very common. So essentially, while this study shows that this possible the periodical behaviors, let's call it this way, is not common, it is still entirely possible, considering the limitations of the analysis, that for a few objects, some periodical behavior, significant periodical behavior is present. And the best case, as I mentioned again before, is this one. This is PG1553. This is a plot that I grabbed from a talk of other people. There are many. It's easy to find these talks on the web. And of course, the sinusoidal red curve is driving the eye, but essentially it is easy to see that you have a peak of activity more or less regular, not completely regular to be fair, but close to be regular. And however, now we have a longer light curves, but if you look at, there are just 4 cycles. So again, a very difficult problem in terms of time series analysis. But it is true that it seems promising. So we decided to try to apply a different tool. And rather than working in the frequency domain, we now try to work in the time domain. Now I will make what I mean hopefully more clear for those of you that are not confident with these concepts. Probably you know, or you have read, that if you do frequency analysis, well, first of all, you can work with the Fourier analysis only when the sampling is perfectly regular. But if we also want to analyze the optical data cannot be observed really regularly. There are periods when the sources are not visible, then you can have bad weather or whatever. There are tools to analyze light curves within regular sampling, as I will show you later. But please allow me not to go in details, because otherwise that would be a completely different seminar. But you can't, in that case, carry out a formal fit of your model for noise to the periodogram, because you have powers that are not independent. Essentially, you have a high correlation between nearby frequencies, and this makes the analysis difficult or not really possible. On the other hand, if we instead go to the time domain, what we essentially are doing, as I'm showing you quickly, we are just carrying out a fit of the light curve with a model with some idea behind. This can be done in a much easier way, conceptually speaking, at least. We are working with Poissonian or Gaussian normal errors. This is again a stronger simplification. And problems like windowing, aliasing, leakage, words that are very common in the frequency analysis domain are not existent, or at least much easier to deal with. The other face of the medal, I'm not really sure that in English they use this word, is simply that typically you need a much more computational power. But you know, today computing power is cheap, and therefore we can try. We try to adopt an idea that we didn't invent at all, but it is quite common in machine learning domain, and the mathematical tool, the statistical tool that we decided to apply is known as a Gaussian process or Gaussian processes. Again, I would be happy to discuss widely about this idea, but I think some example could better explain what it means. First of all, these are the data set that we decided to use. We decided to analyze the two only objects, the two most promising, PG1553, as I showed you before, and PKS2155. We decided to analyze the high energy Fermi lat data, the two plots on the right of this slide, and also the optical data that we have on the left. One interesting point about the analysis that we were carrying out with Gaussian processes is simply that the analysis is essentially independent of the sampling. While, as I mentioned briefly before, if you are leaving the friendly domain of even sampling time series, in the frequency domain, everything becomes very difficult or not possible at all. On the other hand, in the time domain, this is not a problem, essentially. We derived the spectrogram, the periodogram for these 4 light curves. On the right, you always have the high energy, the Fermi data, and on the left you have the optical data, and you see the periodogram with in a solid line, and dashed you have the best fit noise-only model for these curves. And you see these are logarithm plots, so the peaks in the light curves are actually more prominent than they look, but the logarithms helps to see that you have, a power that is increasing with the period or decreasing with the frequency. This is exactly the red-like power noise that we mentioned before. And this is what makes the analysis very difficult. And we have, where you see the vertical line, periodicities that were proposed in the literature that are 2.2 years roughly for PG1553, and the bottom 2 plots, PKS2155, it is a bit shorter, 76 or something like that days. I don't remember exactly, but I can check, but a bit shorter. And the idea is to understand if these periods are really present in the data or not. Now, again, please allow me not to go in exaggerated details, but I'm available to discuss later if you like. A Gaussian process is a sort of generalization of what we typically do. I mean, if you are carrying out a fit, typically you have a set of points, X and Y, and you have a model, a straight line, whatever, and you minimize you maximize the maximum likelihood that essentially, means minimizing the chi-square, the residuals essentially. Now, the hidden hypothesis, not so hidden actually, about this procedure that we use every day is that the data should be independent. Independent means that they are drawn from a statistical distribution that are independent. You can compute the total probability to have your data just multiplying the probability for each single object. This is not exactly, this is correct, but this is not always true. In particular, time series, a time series is exactly a case where you are typically working with data that are correlated. Otherwise, your time series is just a white noise. You don't see any structure. If there is a correlation, you have to change the procedure. It's simple, but you have to describe this correlation modeling the covariance between any pair of data that you have in your time series. This covariance is exactly in the time domain what we call the power spectra in the frequency domain. They are Fourier duals, if I can use this technical expression. So in other words, just to make things simple, you, rather than trying to fit a model for your spectrogram in the frequency domain, and the problems, as you know, are due to the fact that if the sampling is irregular, you can do that easily, and you have to approximate or finding a possible solution basing on very heavy Monte Carlo simulation and so on. On the other hand, if you go to the time domain, you have to model the covariance of the data, the autocovariance of the data. This can be done exactly using Gaussian processes, because a Gaussian process is exactly the way we call this scenario, where when we have data that are normally distributed, but when we also have covariance, not zero covariance between any pair of data points. Again, some technical detail that I've already mentioned.
Stefano, just only to, sorry for interrupting, only to tell you that considering that we were a bit in delay because of the initial so you have about 5 minutes, okay?
Yeah, it's fine. I know. I'm going to the conclusion. Don't worry. And again, as I said, there are there is an equivalence between the analysis in the frequency domain and in the time domain. Again, this is an analysis completely Bayesian. I mean, you can draw any inference basing on the posterior distribution of the parameters of your model, and this is the result. I'm sure that apart from maybe a few of you, you don't really know what you are looking at now, but again, on the right, we have the eigenenergy data. On the left, we have the optical data. And the solid line are, the solid line have the observed covariance in the data. Essentially, you have on the x-axis the lag, and you see the correlation between the data that goes up and down exactly as it is typical for when there is a periodicity. And the dashed line is the model, the covariance adopted in drawing our Gaussian processes. As you can see, apart from one case that I'm going to discuss briefly now, the addition of a periodical component, essentially this cosinusoidal behavior of the covariance, is clearly matching rather well the observed data. This does not happen for the case of the optical data of the PKS2155, the plot on the bottom left, where you see the covariance, the observed covariance, the solid line has nothing to do with the cycling the cosinusoidal behavior of the other three cases. So this is interesting, but what makes the Gaussian processes a very interesting tool is the possibility to, to give a quality factor to measure how important, in a probabilistic way, how favored in a probabilistic way is the addition of a periodical component to the covariance rather than a simple, a different function, the equivalent in the time domain of a power law that is simply describing a correlation that is going down with the leg and nothing else. And you can see the result analyzing the logarithm, let's say the posterior, the marginalized posterior distribution for the period. This is a very amazing plot, I think, because you see these plots are logarithm again. Sorry, it's the logarithm of the probability density function, and we go from 100 days to 2,000 days. This is the limit in periods that we were analyzing, and you see how strong and well isolated and clear are the peaks of the periods for the top row is PG1553, on the left optical, on the right gamma ray, and you see the periods are exactly the same. On the bottom row, you have something interesting in the high energy data of PKS2155, but essentially nothing in the case of the optical data, as I also mentioned before. If you are curious, these are the fit of the light curves with Gaussian processes that are very good, but this is not surprising because Gaussian processes are very flexible. And this idea that we are still developing, because, there are, of course, hidden points, assumptions that can be more or less questioned. However, allowed us to analyze these data sets in a completely different way. And as you probably have already seen, why in the case of PG1553, this periodical behavior is, I would say, convincing. We are still observing probably 5 cycles only, so we are still in a very dangerous domain because, there are many possible phenomena generating transient oscillation that can look periodic only because we are observing them for a short time. But in any case, the evidence begins to be solid, close to 3 sigma, exactly as other people with other tools obtain for this source. In addition, we also have that the same behavior, synchronous, is visible in the optical, although with somehow lower significance. 98% could seem very high, but actually when you are analyzing time series, 98% is not high at all. It's interesting, but this is just a hint of periodicity. But in any case, it is synchronous with the high energy periodicity, and this makes the whole case very interesting. For PKS2155, we essentially have a significance that is lower even in high energy. So again, we have a hint of periodicity, but we have nothing in the optical, and this probably suggests that we are modeling as a periodical behavior just a random fluctuation due to the strong variability of the source that for a few cycles, again, the monitoring is just 10 years long, no more, or 11, whatever, but with the long periods, we have just only a few cycles well covered, and so probably there is nothing significant. And just a final comment. I think I hope I'm respecting the time slot that you have prepared. This is a mathematical result. What does it mean? let's try to understand. What we can say after this work is essentially that the addition, the modeling of the periodogram or the light curve of the autocorrelation, whatever you prefer, adding a periodical component seems well justified by the data. But what this periodical component is a totally different problem. It's a physical problem. And again, it depends on how we try to model the emission from these sources. It can be some irregularity in the accretion that we think it's a periodicity simply because it's something working and maybe slowing down in a much longer time scale than what we can observe. And so for us, it's just a periodical behavior. It can be a real periodicity due maybe to a binarity. This is the most striking, exciting possibility. It is still too early to say. However, as usual, we are physicists anyway, together, I wouldn't say more, together with the theoretical and mathematical consideration, the observations will tell us the truth. In July, it is expected that the new cycle, roughly July, if I remember correctly, the new cycle, the new active cycle of PG1553 should occur. And therefore, the observations of the Fermi satellite on the next summer will tell us if our interpretation is correct or we are just again dealing with a very nasty artifact due to the correlation of the noise as it happens. Actually, it happened already in the past. Okay, this is all. Sorry for the problem with the keynote. I honestly don't know. Probably Google and Apple do not speak to each other very, very, very well. And I hope that at least you have had a correct clue about the complexity of a time series analysis when the situation is not the ideal one with the white noise and so on, and when the signal is anyway low, but also the richness of the field and how promising the possibility to draw a better inferences of the central engines of this source can be possible with a few more years of observations with Fermi and possibly other high energy satellites of the future. And that's all. Thank you a lot, Michele and the other people there.
So
it was a pleasure.
Thank